So what do we do to fix this? What can we do? Any guess? It's simple, huh? Can I change the slope? How do you change the slope? How will you change? All the conditions remain same. You cannot disturb the inductor current.
The control of the gate.
Control of the gate?
FSW.
No. See, I don't want to disturb the inductor current, but remember I am sensing the current. So I can change the slope of the sense current without disturbing the actual inductor current. Ultimately I am feeding the sense current, correct? Change the inductor? How can you change the inductor on the fly? I don't understand. Once you have designed your circuit fixed, I mean this is sitting inside the mobile, so you are going to open the mobile and change the inductor to fix this? I mean, this doesn't make any sense, Okay. So we cannot change the component for sure. All you can do within the circuit, and that also has to be done before you fix your design. Okay. So once you have built the chip, whatever you have done, it will remain there. You cannot make any changes there. So I know this is the sensed current. If you remember, I was sensing the current, and in order to change the slope, and if I want to increase this, which means either it decrease M2 or increase M1, and M2 is the falling. So if I just add extra slope in this, in the rising, or subtract something from M2, then I can always meet this condition M2 is less than M1, correct? So, or alternate way could be, you can do in the sense current, or you can add or subtract that slope from the control voltage itself. It is the same thing, ultimately two things are being compared. Okay, one is lying at the positive, other is at the negative. So if you are adding at the negative, you have to subtract from positive, or other way around. So this is your negative slope. I mean, in this case, if you look, I need to subtract M2 from M2, which means if I have a negative slope and add in M2, that's the one thing. But in this case, I am applying this at a control voltage, so I can basically add a negative slope, which is nothing but subtracting this voltage. So your control voltage now will become like this. So it has a one DC component which is coming from your error amplifier or your compensator, and then on top of that you add this ramp, and this ramp is nothing but same as what you do in the voltage mode control. The only thing, the amplitude of this cannot be much strong. Why? If I make it strong, what would happen?
Peak current will reduce, average current, load current can.
Peak current will reduce, but what will happen in that case?
Average load current will change, so output won't be regulated.
No, average, your control voltage can adjust that, you have outer feedback. So what would happen if, let's say, you add more amplitude, it will start doing this, That's what you are saying, But your outer loop can shift V much up, to get the same current. So your outer loop will adjust that. That's not a problem. The problem is something else here. So if I make this ramp much stronger, then your duty cycle decision is no longer taken by the peak current. Then this ramp itself will decide everything. So you are forcing a ramp now, with your ramp is basically now adjusting the duty cycle, this external ramp, rather than the peak current, inductor peak current, because this is much stronger compared to the sensed current. So your sensed current will die out within that, okay. So because this is more significant. So what happens? If you control the duty cycle with the external ramp, what does it become? Voltage mode control. So the stronger you have this slope, compensating slope, you move towards voltage mode control, then your complex pole pole will start coming into picture and your loop will become unstable. Okay. So, in that case this whatever the type 2 compensator you have designed, that will not work. So, that is why we have to be a bit careful when you are choosing the amplitude of this ramp. It should not be significant compared to your sensed current. Okay. So, now that equation will get modified with this m2 minus m over m1 plus m. So, stronger the m, obviously this will be much lesser compared to the your denominator, and this will converge much faster. But the problem is there is a trade off, whether you want to converge much faster or you want it to behave like a voltage mode control. That is why we cannot make this m much fast stronger. So, what is the ideal case? Ideal case will be m2 equal to m, then it will be 0 and it will settle on just next cycle. This is the case. You disturb and it will just, your falling slope will exactly overlap with the steady state current and it will settle within the same cycle. But it is very hard to design like, so you need to have, because I do not want to have this much lesser, this component. So, that is why you usually little bit overcompensate to take care of the variations, and that is valid for any case actually. And other case could be like, if you keep m1 greater than m2 by 2, then again you will see this numerator will always remain less than that one. But this is a more ideal case where you can get a much accurate value of m. Okay, so this is the same case. So, now if I look at the m2 over m1 ratio, what is that? What is m1? V in minus V out over L, m2 V out over L. So, the two slopes you take the ratio, it will be d over 1 minus d. L will get cancelled out, you take V in common from V in V out. So, V out over V n will become d, and inside you will have 1 minus d component. So, d over 1 minus d, correct. So, this ratio is nothing but d over 1 minus d, and I know my slope compensation. So, from here this equation, if you look at m, so when you add m, if m is greater than half of m2 minus m1, this will always remain stable, correct. So, that is the condition we need to meet. So, now this slope compensation, your basically the compensating ramp slope is required is greater than m2 minus m1 by 2, which is nothing but I will take m1 common and it becomes half of m1 into m2 over m1 minus 1, and I also know that m2 over m1 is d over minus d, which is nothing but v out over v in minus v out. Okay. So, if you substitute this from m2 over m1 from this here, what you get actually half of m1 v in over v in minus v out, or the ratio of these compensating slope to over m1 will be half of v in minus over v in minus v out. And you can also write v in minus v out over L equal to m1, correct, that we know. So, your slope compensating ramp is v in over vL. So, the slope, the compensation slope is nothing but greater than v in over 2L, that is the required, or this. So, if I know the inductor value, which I already know, and I know v in, I can design the slope as a function of v in if L is fixed. So, you get a dynamic compensation. So, I can make this slope compensation varying with v in as a function of v in. Okay. Or if you do not know L, then you can take the information from v out, you can do again the same thing. So, whether L is known, and most of the cases L is known, then you can design. If L is not known, then V in V out is always available. You can take that and do your calculation and design a very accurate compensating ramp. If you fix it, then you have to look for the worst case. So, for the other case, it may be overcompensated. Okay. And overcompensation is not good for any case. I mean, Overcompensation means response time is increased actually for any case. If you want to get a better phase margin, you have to reduce the bandwidth. So, the same thing here actually. If you overcompensate it, then it will may take a longer to converge. So, we want to be closer to the accurate value, and you can very well design this by using this equation, and that is what we call it adaptive slope compensation. Okay. Any questions? So, this was the one important thing to remember when you are designing current mode control. Rest of the compensation type 2 we already discussed, and it looks more behave like LDO, and you can always design current mode control using type 2. But the slope compensation, which is something which is extra in this current mode control, you need to take care of. Current to voltage conversion.
When this compensating slope increases,
Uh-huh.
it becomes a voltage mode. So like I'm still struggling like that.
Okay. So, this is your voltage mode. What do you have? You have an external RAM which does not contain any current information. So, you have a control voltage comparing with a fixed RAM. And what is the slope compensating RAM there? It is a fixed ramp, that is also looking like this. You are forcing a RAM there. Okay. Now, I am adding this RAM to the current RAM. If I add the two and make one much stronger compared to the other, then who will dominate? Obviously, the one which is stronger. So, let us say I make this out of 1, I make this one as a 0.9 and this one as 0.1. So, then your duty cycle will be controlled by this RAM. Now, if I make this guy 0.9 and this guy 0.1, then duty cycle will be controlled by this one. And what do I want in the current mode control? I want duty cycle to be controlled by this, not by this. So, that is why if you might make my compensating RAM much stronger, which will start dominating over this, then it will behave like a voltage mode control. And the moment it start behaving like a voltage mode control, that means you are not able to limit the current. And if I am not having limiting the current, then this inductor will not behave like a VCCS. Now, it will get replaced again by the same inductor, and you will start having this LC pole, resonance, everything, and you need a type 3 in that case. So, that is why we need to avoid that condition when you are designing current mode control.